Okay, so we finished chapter 9, we finished chapter 10. The question some of you are saying is that this is not the trigonometry that I learned. Like, you learn about SOHCAHTOA and right angles, and I'm asking about the sine of negative 225 degrees. So let's talk about the trigonometry that you learned. That's chapter 11, that's right angle trigonometry. The first thing is let's just start off with a basic triangle. So if we have a regular triangle and I ask you about that angle theta, this is, there's two sides that are next to this angle, but there's a third side, and that's the opposite. That's how we're going to decide an opposite side in any triangle. So there's two next sides that are next to it. The third side is the opposite. Now, we're talking about right triangles. So we have a right triangle, and I still have my theta here, and I still have the opposite side. But the question is, how do I describe these two other sides? Now, we're going to call the hypotenuse, once again, it is a right triangle, so we have the hypotenuse. We're going to call the hypotenuse the hypotenuse. And we're going to call the other side that's next to it, we're going to call this, the leg, we're going to call it adjacent. So if you think about it in ninth grade, the hypotenuse was a hypotenuse. So, and we only looked at the acute angles. If you think about it, in right angle trigonometry, you were never asked like what the sine of 90 was, right? Because you were only looking at the acute angles. Okay, now let's tie it into what you know. So we have a unit circle, right? And it was the unit circle, so the radius is 1, and we kind of made a right triangle where the height was sine of theta, right? I mean, it was like, the y was the sine of theta, and the x value was the cosine of theta. So the base here is cosine of theta. Now, let's take a triangle, a similar triangle. By similar, I mean that really all the angles are the same. Here's theta. Here's a right angle. So we know these triangles are the same. So from the perspective of theta, this leg is the opposite side. This side is the hypotenuse. And this side down here is what we're going to call adjacent. Adjacent, once again, is just a fancy word for next to. So because these two triangles are similar, I can make a couple of proportions. And so I can say that the sine of theta over the opposite is equal to 1 over the hypotenuse. Once again, sine is to opposite as 1 is to hypotenuse. And we saw for sine, we got the ratio that you know, which is the sine of theta is equal to the opposite over the hypotenuse. What's another ratio we can create? Let's deal with cosine. So we have cosine over adjacent is equal to, let's take the hypotenuse, 1 over the hypotenuse. And by multiplying both sides by the adjacent, we get the cosine of theta is equal to the adjacent over the hypotenuse. And the last ratio that you recall, that we know is the tangent ratio. And so we can simply say, since we know that tangent is equal to sine of theta over cosine of theta, which is opposite over hypotenuse divided by adjacent over hypotenuse, divided by a fraction is like multiplying by its reciprocal, and we get opposite over adjacent. And this is where the three, so once again, if we start trigonometry off with a theory of functions and we move to right triangles, this is where the ratios that you learn in ninth grade come from. So for example, let's take a look at this triangle, a very basic, a 3, 4, 5 triangle. 3, 4, 5 triangle. And I'm going to call the acute angles theta and beta. And so you can find the sine, cosine, and tangent of theta and beta. So the sine of theta, you're standing at theta, and you're saying, okay, 4 is opposite, 5 is the hypotenuse. Now I'm asking you for the cosine of theta. You say, you know what, Mr. Aller? I'm standing at theta, 3 is adjacent, 5 is the hypotenuse. And we can look at the tangent of theta, opposite over adjacent. And you can clearly go through the other angle. If you're standing at a different perspective, now I'm asking you to stand up here. Now what's opposite? Well, 3 is opposite beta, so the sine of beta is 3 over 5. Please remember, when you're asked for the sine, cosine, tangent, cosecant, secant, cotangent, these functions of an angle take you to a ratio. So the cosine of beta is 4 over 5, and the tangent of beta is 3 over 4. Another thing you might be asking is, what are these angles, by the way? And, we'll get to that in a second. So, some of the word problems that you did in 9th grade trigonometry were, here's a triangle. Here's a triangle, a right triangle, and the acute angle down here is 23 degrees, and the height is x, and the hypotenuse is 12. Find x. And so you say, okay, once again, if it's 23 degrees, I need a calculator. So you say, if I'm standing at 23 degrees, x is opposite, and 12 is the hypotenuse. Well, opposite over hypotenuse, I would use the sine ratio. So you'd write sine of 23 is equal to x over 12. How do I undo division? So multiplication, so x equals 12 sine 23. Please make sure you're in degrees. Answer 4.69. Another example with a little algebraic twist. We have a right triangle. The base angle is 71 degrees. The base is 15, and the hypotenuse is x. How do we solve that? Well, you're standing at 71 degrees, and you're in a right triangle. You say, you know what? 15 is adjacent. X is the hypotenuse. Therefore, I'm going to use the cosine ratio. So the cosine of 71 is equal to 15 over x. Now, this may seem a little tricky. If you think about it, we have x cosine 71 equals 15. Therefore, x equals 15 over cosine 71. Please be careful. Also, please remember, when you put this in the GDC, you have to put the degrees in parentheses. Last but not least, if you're given two sides, how do I find the angle? Very easy. How about this? So, here's theta, and I made up a problem. The height, it's a right triangle, the height is 9, and the hypotenuse is 17. How do we figure this out? Once again, if I'm standing at theta, I have opposite over hypotenuse. The sine of theta is equal to 9 over 17. Well, how do I undo? If the sine of theta equals 9 over 17, then theta is equal to sine inverse of 9 over 17. Hit math, and you'll see sine inverse. Once again, please remember to be in degrees. The answer is theta is approximately 32.0 degrees. Nice. A couple of other things you learned before we move on is something called the angle of elevation and the angle of depression. The angle of elevation is simply this. You're standing here. You're looking straight ahead. there's something in the sky. You move your head this amount of degrees, that's the angle of elevation. Or you're standing on the top of like a light post, or you're guarding, and you're looking straight ahead, and you notice something down, and you look down. That's the angle of depression. So let me make a diagram. So you're a person here, you're looking straight ahead, and you look up in the sky. That angle is the angle of elevation. Versus you're standing on some type of like you're guarding something, and you're looking ahead, and you notice something here. You look down. This is the angle of depression. Now, you might have learned that the angle is, if you're looking, if let's say these are the same people, so the idea is that you might have learned is that if the same person is looking down at you, their depression is equal to your elevation. Same idea here. If you're on the ground and you're looking up at them, your angle of elevation is equal to their angle of depression. That was the connection, but the black is the important part. Next, let's move on. What's next? Okay, so area of a triangle. Now, we've already learned that the area of a triangle. So what is the area of a triangle? We know that it's 1/2 of the base times the height. And that's fine, and we're doing right triangles. Now, if you remember, after you did all this, like the unit kind was over, as in like that was it. Maybe you were in an advanced class, but the idea is that right angle trigonometry is over. We're done. Well, I want to use trigonometry to expand. And so the question, I want to find the area of a triangle. So you say, fine, the area of a triangle is 1/2 the base times height. That only applies if it's a right triangle, or you have the base and you're given the altitude. Well, what if you're not? So let's take a triangle. Excuse me. Let's take a triangle. And I have angle C, and I have side A, and I have side B. Okay, the question is, how do I find the area of, is this enough to find the area of a triangle? I'm going to say yes. First of all, if I give you two sides and an included angle, this triangle is unique. Next, the next thing I want you to do is drop an altitude. And so I don't know what the altitude of this triangle is because it's no longer a right triangle. Let's call this H. Okay, well, my question to you is, what is the height? So you say, well, if I'm standing at C, I have the opposite and my hypotenuse. Therefore, I know that the sine of C is equal to H over B, which means that H is equal to B sine C. Therefore, the area of any triangle is equal to 1/2 the base times the height. And so we now have a formula for the area of any triangle, given you got two sides and the included angle. So I can make up a triangle right here. Here's a triangle. It's 5, 70 degrees, and 10. And you say, no problem, Mr. Adler. The formula, I have two sides and the included angle. So you're like 1/2 times 5 times 10, sine of 70. Please remember when you put this in the calculator, the 70 has to go inside the parentheses. You hit enter, and the answer is 23.5. Whatever the units are, don't bother me. I mean, I guess I should, but let's say this is centimeters. So this is square centimeters. Nice. Now, we're advanced math, so we have to deal with another problem. And so I say to you, let me erase this board. I say to you, if I give you two sides of the area, can you find the included angle? For example, I say that we have a triangle here, and I'm telling you that the two sides are 8 and 9, and the included angle is theta. Now, for your calculator, if you want to use, let's use a letter. Let's start with the letter C, because we've been using C, but you can use any letter you want. And so I'm telling you that the area is 30 meters squared. Can we find angle C? What is angle C? And you say, no problem, because I have the formula here. There's 1, 2, 3, 4 variables, and I have 2 of the sides and the area. So all I need to do is just find C. That's one unknown. One equation, one unknown, perfect. You're like, okay. So I have 1/2 times 8 times 9 times the sine of C is equal to 30. No big whoop. You're like, that's no problem, Mr. Adler. This is what 8 times 9 is 72, divided by 2 is 36. So it's sine of C equals 30 over 36. And some of you might say, hey, you can reduce this to 5 over 6. No big deal. But there's an issue. Not a problem per se, but there is an issue. Well, can anyone guess? Very good. Sine is positive in the first and second, which means there's 2 angles that will make this true. And so you go to because sine of C is greater than 0 in the first and second, C is in the first and the second. So so C equals inverse sine of 5 over 6, and you get 56 plus 4, but also 180 minus 56.4, which is what? 123.6. So you have to be careful with sine. I'm not a big fan of sine. I love cosine more, but as long as you know that you're going to have 2 answers here, you can actually have we can create 2 triangles. One 56.49 has an area of 30, and technically an 8, 9, 123.6. This triangle also has an area of 30. So with sine, when you get down to the equation, sine of C equals something, you have to be careful. Okay, and then let's try one more example. Another example is, try this one. I tell you that we have a triangle, and I don't know what it looks like. This is probably a really horrible diagram. I don't know the angle. I know that 5, 4, and I'm told, someone's telling me that they want sides of 5 and 4, and they want an area of 50 meters squared. And so you say, okay, no big deal. It's a formula. I just have to plug the numbers in the formula. So let's see what happens. We get 1/2 times 5 times 4 sine of theta equals 50. And so 5 times 4 is 20 divided by 2 is 10. So you're like sine of theta equals 50 over 10, which is 5. Can anyone see what the problem is? Can anyone see what the problem is? So there's no answer. Because we know that sine of theta is less than or equal to 1. So there's no answer. This is not possible. Okay, let's move on. So, next thing we want to do is we want to extend this a little bit more. Now that we've actually moved past right angle trigonometry, we can work with any triangle. So let's explore the relationship of the sides of any triangle. Well, let's start again with my diagram. So this is the law of sines. Okay, so let's start over again. We have a triangle, C, A, B, right? And then technically I could fill these other sides in. I could call this, this is little side C, this is big B, and this is big A, right? Now, the area here was 1/2 AB sine C. Now, I'm going to say, take this triangle and rotate it. So I'm going to rotate it. So it now looks like this. So now B is over here, C is at the bottom, and A is along the side. Well, we know, actually we didn't discuss it. Rotation is an isometry. And when I say isometry, it means area doesn't change. Does not change. Yes, area doesn't change. So technically, the area now is also 1/2 AC sine B. And I could rotate this again. I could rotate this triangle again. And now A is in the corner, B is in the base, and C is on the side. And so the area of this triangle is 1/2 BC sine of A. Well, we did a rotation. The area didn't change, which means these three equations are equal to each other. These three equations are equal to each other. So let's write this out. 1/2 AB sine of, sorry, hold on a second. I apologize. 1/2 BC sine of A is equal to 1/2 AC sine of B, which is equal to 1/2 AB sine of C. Now, how can I simplify these three equations that are all equal to each other? Well, what we're going to do is we're going to divide every single term by 1/2 ABC. Well, if I take out the half and the BC, I'm left with sine of A over A. And if I divide the second term by 1/2 ABC, I get rid of the half, the A, and the C, and so I have sine of B over B. And the last is the sine of C over C. And this is kind of cool that this is a relationship among the sides and the angles of any triangle, that the sine of an angle divided by the ratio of the sine of an angle over its opposite side is proportion. And that's kind of cool. So this is kind of cool. So given two angles and a side, you can find the missing side, find the side. Or given two sides and an angle, you can find, given two sides and an angle, you can find the other angle. Let's go to the problem. Obviously, because they're sine, obviously we're going to have some issues, but it's no big deal, right? Let's see. Example 1. I have a triangle here. It's 17, 14, 47, and I want to find this angle. Let's call it D. Question is, are we going to have the issue with the sines? And you go, oh, you know what? Sorry, I apologize. Let's change this a little bit. Let's make this 80. Sorry. We're going to change to 82 degrees. I'm going to ask you to find x. So Are we going to have an issue with sine? You're like, no, because you give us both of the angles. And we know from geometry that this triangle is unique because of angle, side. So you say, fine, I have the 47 degrees and the opposite side. I have the 82 and the opposite side. Law of sines. You're like, fine. Sine of 47 divided by x equals sine of 82 over 17. I don't want you cross multiplying or solving. I just want you to get this formula down on the paper and then use solver to solve this. Old school, they make you solve it, cross multiply and then isolate the x. I'm not making you do that. The answer is, what is the answer? Oh, I think I changed. So let's see, sorry. Sine of 47 divided by x is equal to the sine of 82 divided by 17. Final answer is 12.6. Okay, so those are easy. So if you're given, angle, side, it's easy. It's fine. There's no problem. But this is higher level. So we need to address the problem, the question that might give us problems. Okay, so let's see. The problem I'm going to look at is, let's see. Here's a triangle, and we have a 17, 14, and 47. And so the question is, given theta, let's call it E. Right? The question is, what is that angle? And so you should get suspicious. You say, wait a minute, Mr. Eiler, side angle? That was not one of the rules we were able to prove triangles congruent. So there's a possibility that there's two different triangles that have 47, 17, 14. Maybe it looks like this. Maybe here's 14, 7, 47. There's a possibility that there's two triangles with these characteristics. No big deal. So let's set this up. So I know that 14 is opposite 47, E is opposite 17, law of sines. So the sine of E divided by 17 is equal to the sine of 47 over 14. Take your calculator out. And we know that sine is equal to 62. But we know that the sine is positive in the first and the second. So it's also 180 minus 62, which is 118 degrees. Now, that's fine. So you say, okay, Mr. Adler, there's two triangles, and they're fine. No. The problem is you have to check the results. So you must check. You're like, fine. Let's assume there's two triangles. Triangle 1, triangle 2. And let's call the angles A, B, and in E. Well, no. Let's call the sorry about that. We have angle E, right? That was 62 and 118. We had an original angle, which was, let's call it A, and that was 47, right? The question is, let's call the next one E. Is it possible that there's a third angle here? Once again, I could draw anything I want. It might not be real. But you say, you know what, Mr. Adler? No, it's fine. Because this is 180 minus 109, so it's 81 is for the third angle. And over here in the second situation, 180 minus, well, what's 118 plus 47? That's 165. So the other angle is 15 degrees, and therefore it is possible that we can make two triangles with a 47, 17, 14. Is there an example where this doesn't work? Yeah, let's check that one out. So that example, this is the last example. We've done a lot. We've done like 4 or 5 units already. The last example, a 60, 11, 15 triangle. 60 degrees, 11, 15. 11, yeah, 15. So you say, and I ask you to find angle F. And you're like, okay, no big deal, Mr. Adler. Law of science. I have a side opposite F, and I have a side opposite 60. If you're missing an angle, fill in the angles. Remember, the angles of a triangle are 180 degrees. Well, let's get to this. So you're like, fine. You're like, sine of F over 11 is equal to the sine of 60 over 15. You do your calculator, you said F equals 39.4. But then you say, no. F could also be 180 minus 39.4. Which is what? What is that? That is 140.6. Okay. And then you say, let me see if these two triangles work. Because in the last problem, I had two triangles that worked. So we have triangle 1 and triangle 2. Okay, and first let's call this A. So this is 60. Let's call this next triangle F, 39.4, and 140.6. Well, maybe they'll ask so you say, okay, let's call this, I don't know, G. AFG. And so this one is 180 minus 99.4. You're fine with that. That's, what is that, like 80.6? Yeah, 80.6 degree. What's going on here? Well, this sum is greater than 100, this is 200.6. That's no good, because a triangle can only have 180 degrees. So this is the problem you come into with area of a triangle and law of sines. They both involve sine, therefore you have to be careful that you acknowledge that there's two possible answers. And I think that's it. We're good.